Derivatives of some particular functions. We'll have a look at the trigonometric functions and the exponential function e to the x. Here are the two standard trigonometric derivatives. Derivative of sine is cos, derivative of cos is minus sine, and from there we can derive the rest of them. There is a standard difference between two terms, so when we differentiate that, we differentiate the first, we differentiate the second. 2x minus cos x. There's the rule. There's a product, derivative of x cos x. So we have 1 cos x plus x times minus sine x, which simplifies to that. Derivative of the first times the second plus the first times derivative of the second. There we are. X goes to 1, x stays as x, cos stays as cos, cos goes to negative sine. A quotient rule. Top sine bottom x squared. There's the rule. Derivative of top, bottom minus top, derivative of bottom, bottom squared. Here we are. Derivative cos stays, minus stays, derivative 2x all over that squared, which simplifies to that. This is a composite function. It's chain rule. Outside function cos, inside function 2x plus pi. Therefore, we're going to differentiate the outside function times derivative of the inside. Equals derivative of cos minus sine, and 2x plus pi stays as 2x plus pi, times derivative of that 2. And that simplifies to minus 2 sine 2x plus pi, just to be mathematically neat. Now we have 4 other trigonometric ratios. Tan, we know. Cot, the inverse of tan. Sec, the inverse of cos. Cosec, the inverse of sine. Let's prove these. It'll give us a bit of practice using trigonometry with the rules of differentiation. Derivative of tan. Now the only derivatives we know at the moment are these, so we need to write that as sine over cos. Now that is a quotient rule. So we get a differentiate times cos minus sine times differentiate all over cos squared. There we are. That simplifies to cos squared plus sine squared over cos squared. Top line, that is the Pythagorean identity, equal to 1. So therefore we're going to have 1 over cos squared. And that is, of course, sec squared. There's our derivative. Next one, derivative of cot. We're going to write that as cos over sine. Quotient rule, derivative sine minus cos derivative over sine squared. Now if we take out a minus to put in front of the fraction, we'll end up with sine squared plus cos squared. That is 1, so it's 1 over sine squared, and that becomes cosec squared. Negative cosec squared. Sec is the inverse of cos, so we write sec as 1 over cos. Now we can use the chain rule, because we're going to write that as cos x to the minus 1. Differentiate the outside, minus cos x to the minus 2, times derivative of the inside, minus sine, which gives you minus sine over cos squared x. The minuses have gone. Negative exponent, so it goes to the bottom. Now I'm going to recognize from that we can have a sine over cos and a separate 1 over cos. So that'll be my 1 over cos, sine over cos, and that is sec times tan. We're going to write that as 1 over sine, which means sine to the minus 1. Differentiate it using chain rule. Negative exponent goes to positive exponent. We're going to take cos over sine times 1 over sine, and that'll give us cosec times cot with a negative. Let's have a look at chain rule now with a couple of trigonometric functions, particularly functions that do cause problems sometimes. For example, this is sine of x squared. Notice that the x is being squared, not the sine. So the outside function is sine. The inside function is x squared. So we differentiate the outside function. Sine of something becomes cos of that something, times derivative of the inside. Let's be mathematically neat. Now let's look at sine squared x. Now that's different because now it's the sine of x being squared. So the outside is something squared, the inside is sine. If we differentiate 2 sine x, so that's derivative of the outside, 2 times this to the 1, and times derivative of the inside, which will be cos, derivative of sine, and that there is the double angle formula, so it's sine 2x. Let's have a look at some examples. Here we are. The first one's just purely a sum. Differentiate, differentiate. There we are. Next one. Write that with negative exponent, and then it's a sum again. There we are. Differentiate, and then get rid of negative exponent. Next one. That's fine. This we must write with the exponent to a half. So therefore we're going to do that. Now when we differentiate, that's going to give you your negative cosec cot. That's going to differentiate in the standard fashion, and that's going to go. So we're going to end up negative cosec cot for the cosec, minus 2x to the minus half, which we then write back with a positive exponent. 4 minus x squared sine x. Now there we have a product rule. When we differentiate, that 4 is going to go. That negative is going to stay, and we're going to have to use product rule here. Derivative of the first times the second plus first times derivative of the second. So I put it in brackets. The 4's gone, the minus there. That red part there is the derivative of that using product rule. 2x sine x plus x squared cos x. And that can simplify to there. Another one. Here's another product rule, and then write this as x to the minus 2. So there we are. So now derivative times that plus that times derivative. Here we are. The one in red is the product rule. 2x times cot plus x squared times derivative of cot is minus cosec squared. That becomes plus 2x to the minus 3. Now what we do is we simplify this a little bit, and we write with a positive exponent. This one. Right, the easiest thing to do here is to multiply it out first. I like this idea of cos times sec because they are inverses. So when cos times sec multiply, you're going to get 1. So you're going to have sine sec plus 1. And there is a product. So now we use product rule. Derivative cos times sec plus sine times derivative sec times tan. Differentiate the 1, it's gone. Of course, cos times sec is 1, and we're left with that there. We could write in other forms as well, but I'll leave it like that. There's not much simplifying. Sine over cos, 1 over cos, sine, nothing's going to cancel. Right, this one, here is a quotient rule. There we are. Derivative of the top minus sine times the bottom minus top times derivative of the bottom, and the bottom's derivative will be just straight cos over bottom squared. That simplifies to that, which of course we can continue now, because if you're observant, minus sine squared minus cos squared is minus 1. We can take out a common factor, and there it is there. And if you observe further, you will see that that is the negative of 1 plus sine, which we have below. Therefore we can do a teensy-weensy bit of cancelling, and we end up with that as an answer. That negative comes from the minus minus coming out. There's the minus. Next one, straightforward product rule. Derivative of the first, notice that extra 3, because when you differentiate this first, you'll get cos 3x times derivative of the inside times cos 2x plus sin 3x, and now derivative of that is minus cos 2x, minus sin 2x, times derivative of the inside. And that simplifies to that. One last one. This is a chain rule. Cos of cot. Outside function cos, inside function cot. So we're going to say minus sine of cot, inside stays the same, times, and then the derivative of cot is minus cosec squared. And there is our final answer. Let's have a brief look at the exponential function. Very fascinating one, this, because the derivative of e to the x is e to the x. E is a magical number with all sorts of properties, but e to the x, y equals e to the x, is in fact its own gradient, its own derivative, which means it's its own gradient. So, if we have to differentiate that, that is a composite rule. That's a chain rule, because the outside function is e to the something, the inside function is minus x. So therefore, e to the minus x, outside function e to the anything stays e to that something, times, now we differentiate the inside, minus 1, which becomes that for mathematical neatness. Next one, e to the something, so there's your outside function, and it'll stay e to the something, and then you must differentiate the inside function. So there we are, e to the sine x, and then the derivative of sine is cos x. Let's have a look at a few examples here now too. There we are, y equals e to the minus 5x. The outside function is e to the something, so it stays e to that something, and then we differentiate the minus 5x. So that's how we end up with e to the minus 5x times minus 5. E to the 5 minus 7x. So we're going to get back e to the minus 5 minus 7x, because e to the something differentiates straight back to the same thing. And then we multiply by the derivative of the inside. So there we are, e to the 5 minus 7x becomes e to the 5 minus 7x times differentiate 5 minus 7x minus 7. E to this one now. This one we're going to have to write that with fractional exponent. There we are. Now, when we differentiate, we're going to get straight out with that, and then times the derivative of that. There we are. This comes straight back at us, and then derivative of half 4x to the half becomes 2x to the minus half minus 2x, and we could go a step further. We should, but I was too lazy. Next one, this one here. Right, there's a product rule. X times e to the x, derivative of the first times the second plus the first times derivative of the second, and then we differentiate that. There we go. That there is the derivative of x e to the x. Derivative of x, e to the x, derivative of e to the x. Now you have e to the x minus e to the x, so we end up with just minus xe to the x. Right, last one. Also a product rule. Differentiate, leave as it is, then leave as it is, differentiate. There we are. Now I'm sure there are going to be some like terms collecting up inside here somewhere, like there's a 2x e to the x, there's a minus 2x e to the x, there's a minus 2e to the x, and there's a plus 2e to the x. So it looks like poor old x squared e to the x is going to be left on its lonesome. There it is there.